guys, welcome back to my channel Techno Education Academy. In this video lecture, we will derive the equation of efficiency for Rankine cycle. First of all, what is the application of Rankine cycle? Thermal power plant, it will work on Rankine cycle. Thermal power plant means it is a coal-based power plant in which we are using coal as a fuel. In India, most of the power plant is thermal power plant and it will work on Rankine cycle. Basically, there are four components in Rankine cycle. The first one is boiler. Boiler, it is a closed pressure vessel. Okay, it must be in closed condition. Okay, we have already discussed classification of boiler, various types of boiler. Okay, in my playlist, you can watch it if you want to clear your fundamental. What is boiler and classification of boiler according to IBR. So boiler is a closed pressure vessel in which we supply the heat energy, okay, through any types of fuel. But in thermal power plant, we are using coal as a fuel. So by the combustion of coal, here we supply the heat energy, and this boiler, it will generate the steam. It might be superheated steam, wet steam and dry steam. It will depend on heat supply. Okay, how much amount of heat is supplied to the boiler, so it will generate steam. So here you can see that 4 to 1 process. Okay, here you can see that at point 4, okay, it is a liquid, or we can say water. It is enter into the boiler through the feed pump. Here you can see that, okay, on left hand side of the dome, okay, it is a liquid region. Middle portion of the dome, it is a liquid plus vapor region, and on right hand side of the dome, here you can see that this is a gas region. Okay, here you can see that this is a dome. Okay, on left hand side of the dome, it is a liquid parts. Liquid portion is there, and middle portion of the dome, here you can see that the liquid plus vapor is present, and right hand side of the dome, here you can see that the gas particles are there, or the gas forms or gas region is there. So in a boiler at point 4, okay, it is represented here because it is liquid form. Okay, it is the entry of the boiler, or we can say here we enter the feed water through the feed pump. And in a boiler, the heat supplied is constant pressure. Okay, in a TS diagram, the constant pressure is represented by this line. Okay, this 4 1 dash 1 1 double dash, it will represent the constant pressure process in the boiler, and this portion, it will represent the liquid portion. The middle portion of the dome, it will represent the mixture, liquid plus vapor, and the right hand side of the dome portion, it will represent the gas region. So at point 4, the water particles, so at point 4, the liquid will enter through the feed pump in the boiler. Here the heat supplied through the coal, or by the combustion of coal, so it is converted into wet steam, dry steam and superheated steam. So here you can see that 1 dash, okay, it will represent the wet steam. Okay, when we know that the boiling point of water is 100 degrees Celsius. So at 60 degree, some moisture is there. At 70 degree, the moisture content will be decreases. At 90 degree, again the moisture content will be decreases. So this portion, it is represented by the middle portion of the dome. So at 100 degree, the total moisture is removed. It is called saturated steam, and it is represented at point 1. And whenever we supply the more amount of heat energy, then it is converted into superheated steam. So this point will represent the superheated steam, and it is used in the thermal power plant, and it will obey all thermodynamic law, because we know that the superheated steam, it also behave like a gas. Then after this steam, it is expanded in a turbine. As we know that turbine is a expander. Okay, so theoretically in a turbine, the process is isentropic, but practically it is adiabatic process. We have already discussed in my previous playlist of engineering thermodynamics. Okay, we have already discussed different types of non-flow processes, adiabatic and isentropic. So what is the difference between adiabatic and isentropic? If adiabatic, it is reversible process, then it is called isentropic process. Isentropic means the entropy remain constant. So in isentropic process, throughout the process entropy remain constant. But in adiabatic process, okay, it is an irreversible process. Means some irreversibility is there due to some internal friction in the process, some heat rejection is there. Okay, so this is called irreversibility, and this irreversibility is due to internal friction in the process and heat rejection. It is called adiabatic process. And isentropic process means entropy remain constant. So here we will discuss ideal Rankine cycle. So here we are considering isentropic expansion in a turbine. So this vertical line, it will represent the entropy remain constant throughout the process in a turbine. But we know that turbine is a expander. So whenever the steam will be expanded from one double dash point, so some moisture content will be there because of the increase in volume. Okay, the pressure of the steam, it will be decreases, so temperature is also decreases. So this point, it is represented in middle portion of the dome. Then after this steam, it is enter into the condenser. As we know that condenser means what? It is a heat exchanger, and in a condenser, okay, there is a latent heat will be transferred. Okay, basically there are so many needs of the condenser in the thermal power plant. By using the condenser, okay, you can increase the efficiency of the boiler, because we know that the volume of the steam is 1600 times. Okay, so it will occupy more space. So here we need compressor, and we know that the compressor, it will consume more power. But here we are using pump, and pump is only convey the liquid. So this steam, it is coming out from the turbine, it is condensed in the condenser. Okay, we will discuss later on what is the basic need of condenser in the thermal power plant. So the basic or the important role of the condenser, it will improve the efficiency of the thermal power plant. It will increase the efficiency of the thermal power plant. Okay. So here the latent heat will be transferred. Latent heat means temperature remain constant, and the phase transformation will be take place. So here you can see that throughout the process, the temperature remain constant. Here you can see that it is represented by horizontal line, temperature constant. Then after this condensate, it is conveyed through the pump, and ideally in a pump, the process is isentropic compression, but practically it is adiabatic. So here we are represent the process in a pump. It is through vertical line, because vertical line will represent the entropy remain constant, isentropic compression in a pump theoretically, but practically it is adiabatic. Here we derive the equation based on ideal Rankine cycle. Okay, so these are the four processes. It is occur in different component of the thermal power plant, or we can say Rankine cycle. This is a PV diagram. This is just for your reference, and this is HS diagram, enthalpy versus entropy diagram for Rankine cycle. Now we will derive the equation of efficiency for Rankine cycle. Here we are considering steady flow. Okay, in each and every component, okay, of the Rankine cycle. So here we apply the steady flow energy equation. All four components associated with Rankine cycle steady flow devices, and hence this process can be analyzed steady flow process. So we have already derived the steady flow energy equation in my previous lecture. Okay, you can visit my playlist and watch it how to derive steady flow energy equation. Okay, for turbine, nozzle, heat exchanger, boiler. Okay, we have already derived it in my playlist. If you want to clear your fundamental, then you can visit this playlist and watch these videos. So this is the equation of steady flow energy equation, H1 and H2. It is the enthalpy at inlet and outlet. C1 square by 2 and C2 square by 2. Here we are considering mass is 1 kg. Okay, or we can say here we are considering specific property. So we are not considering, we are not multiplying mass, okay, with each term. So 1/2 mv square, as we know that it is a kinetic energy. So it is the kinetic energy at inlet, kinetic energy at outlet. enthalpy at inlet, enthalpy at outlet. Okay, this is the potential energy at inlet side and outlet side. Q is the heat transfer, and W suffix S, it is the work done. But here we are neglecting kinetic energy and potential energy. Okay, so this is the simplified form of the steady flow energy equation whenever we neglect the kinetic energy and potential energy. So the remaining term is enthalpy at inlet and outlet, initial enthalpy, final enthalpy, heat transfer, and work done. This is the remaining term, and this is the steady flow energy equation. It is written in simplified form whenever we neglect the kinetic energy and potential energy. Now we will derive the equation of efficiency by considering the process one by one. Process 4 to 1, it is a constant pressure heat addition process. Okay, I have already discussed or mentioned, in a boiler the heat supplied is at constant pressure. So constant pressure means throughout the process the pressure remain same. So the water is heated at constant pressure in the boiler until the saturation temperature is reached. Saturated water is converted into saturated steam at constant pressure. During 1 to 1 dash process, steam is superheated in superheater. Okay, as we have already discussed, superheater, it is a device which is located in the combustion chamber side, and this superheater, it will generate the superheated steam, and this superheated steam is supplied to the turbine. We have already derived it, this equation, whenever we neglect the potential energy and kinetic energy. So as we know that boiler, okay, in boiler we supply the heat energy, but in a boiler it is not an output device. Turbine is an output device, boiler is not an output device. So the simplified form of this steady flow energy equation, whenever we apply this equation to the boiler, so heat transfer equal to enthalpy difference H1 minus H4. Final enthalpy at point 1, initial enthalpy at point 4, because in the boiler 4 point it is the inlet and 1 point it is the outlet. So heat supplied equal to H1 minus H4. Same as for process 1 to 2, it is occur in the turbine, isentropic expansion in the turbine. High pressure and high temperature superheated, dry saturated or wet steam generated in the boiler at P1 and T1 is supplied to the steam turbine. It is also known as an expander. Okay, and it is an output device. Whenever the steam will be expand, so at that time the volume of the steam will be increases and the pressure is decreases. This steam expand isentropically into steam turbine up to the condenser pressure. We have already discussed what is the need of condenser to increase the efficiency of the thermal power plant. Okay, and in the condenser, okay, it is a heat exchanger. The latent heat will be transferred. The temperature remain same, and the phase transformation will be take place. So whenever we apply the steady flow energy equation to the turbine, okay, generally turbine is totally insulated, so there is no any transfer of heat, okay, to the surrounding, and here the work done equation equal to H1 minus H2. Process 2 to 3, constant pressure heat rejection in the condenser. The exhausted steam from turbine enters into the condenser, where it is condensed at constant pressure by circulating cooling water into the tubes. Okay, as we have discussed, it is a one type of heat exchanger. Okay, and it is used in the thermal power plant to increase the efficiency of the plant. Okay, and here we are using cooling water. Okay, for the heat transfer. The heat rejection by exhaust steam, it is represented by Q suffix R, and whenever we apply the steady flow energy equation to the condenser, as we know that condenser is not a output device, so there is no any work will be produced in this device, but only exchange of heat. It will reject the heat. Okay, so QR equal to H2 minus H3. Same as process 3 to 4, it will occur in a pump, and pump is used to convey the condensate from the condenser to the condenser outlet, and pump is used to convey the condensate from the condenser outlet, or we can say from the hot well to the boiler. Okay, and as we have discussed, okay, in a condenser there is a latent heat will be transfer. So whenever we supply the hot condensate to the boiler, so it will reduce the fuel supply in the boiler. You can also consider the one example, whenever we boil the water from the solar water heater. Okay, and same as whenever we boil the water from the normal temperature, so the solar water heater, it will boil fast because it is available at high temperature. Same as the outlet of the condenser, it is available at high temperature, and whenever it is supplied to the boiler, so at that time we supplied less amount of heat because it is available at high temperature, so that our fuel supply, it will be reduced by using this component, or we can say condenser. So condenser is used in the thermal power plant to improve the efficiency of the thermal power plant. Okay, it will increase the efficiency of the thermal power plant. So the condensed water coming from the condenser is pumped to the boiler at boiler pressure with the help of feed pump. Okay, and whenever we apply the steady flow energy equation, and we know that pump is a work input device. Okay, and here we neglect the heat transfer. So work done, work input in the pump. Okay, it is a output device. Remember, friends. Okay, turbine is a output device and pump is a input device. Okay, turbine will produce the power and pump means it will consume the power to run this device. So here we require the energy, okay, or work done, okay, to run this device. So work done in the pump equal to H4 minus H3 in terms of enthalpy equation. So efficiency of the Rankine cycle. Efficiency means output upon input. This is the general term of any efficiency equation. So thermal efficiency means net work done divided by heat supplied. For this device or for this cycle, okay, what is our output? Turbine work. What is our input? Pump. It is a device to convey the liquid from output of the condenser, from the outlet of the condenser to the boiler. So pump is a device to convey the condensate from outlet of the condenser to the boiler. So it is a work input device, it is work output device. So net output means output turbine work minus pump work. Okay, so this is net work done. And heat supplied, it is the input in the boiler through the combustion of the coal. Here we supply the heat energy. So efficiency of Rankine cycle equal to net work done divided by heat supplied, and net work done means WT minus WP, turbine work minus pump work, divided by QS, heat supplied in the boiler. So heat supplied to the working fluid in a boiler during the process 4 to 1. We have already derived this equation, QS equal to H1 minus H4 in previous slide. Turbine work during process 1 to 2. We have already derived it in previous slide, H1 minus H2. Heat rejected during condensation process 2 to 3. We have already derived it, QR equal to H2 minus H3, and pump work during process 3 to 4 equal to H4 minus H3. So net work output means turbine work minus pump work, WT minus WP, because this is an output device and this is an input device. So net output is WT minus WP, work output device, and work consumed device, consumable device, work input device. So work output device minus work input device. So net work done equal to work done in turbine, H1 minus H2, and work done in pump equal to H4 minus H3. Now we will put the value of heat supply and work done in equation of efficiency of Rankine cycle. So put these two value in this equation, we are getting efficiency of Rankine cycle equal to net work done H1 minus H2 this is turbine work, minus H4 minus H3, this is pump work. Work output minus work input, divided by heat supplied in the boiler, H1 minus H4. Further, we simplified this equation. Here we rearrange the enthalpy term, and we are getting H1 minus H4 minus H2 minus H3 divided by H1 minus H4. Usually pump work is very small and hence it is neglected. We are getting efficiency of Rankine cycle equal to 1 minus, okay, this term is separately divided with this term. So efficiency equal to 1 minus H2 minus H3 divided by H1 minus H4. And whenever we neglect the pump work, okay, then we are getting this equation, H1 minus H2 divided by H1 minus H4, whenever we neglect the pump work. Okay, at that time, this is the equation of efficiency for Rankine cycle, and whenever we are considering the pump work, then we can use this equation for the Rankine cycle. So thank you friends for watching this video. I hope this content it will be helpful to you. If you would like to watch this type of more technical videos, then please subscribe our channel and also share with your friends.